Thank you very much, and thank you very much to Johannes and Al for organizing this wonderful seminar series. Today I'd like to talk about some recent joint work with Fatemeh Mohammadi, my supervisor, and Akihiro Higashitani. So this will be about matching field polytopes, combinatorial mutations. So if these are all very new words to you, I'd like to give you a big picture overview of what this research is about. So we're going to be looking at toric degenerations of this variety called the Grassmannian. We can think about this as some projective variety. And associated to it, we have a collection of points in the tropicalization of the Grassmannian. Tropicalization you can think of as some combinatorial shadow of this variety. And these points give us matching fields. And if you choose your points well enough, you can obtain some toric varieties through some process called Gröbner Degeneration. And associated to each of these toric varieties is a polytope. And using the data of the matching field, which is not just the point in tropicalization, it's a little bit more, you can write down some polytopes. And in this research, we're going to be looking at combinatorial mutations that turn out to connect many of the polytopes, which we already knew about coming from toric degenerations of the Grassmannian. And what do these combinatorial mutations look like? They're sort of restrictions of what we call tropical maps. So what I'd like to do in this talk is talk through most of the parts of this picture. So I'll begin by talking about combinatorial mutations and polytopes. Then we'll look at toric degenerations and the Grassmannian. And finally, I'll explain how what our results look like, which are going to show that many of the polytopes are connected via combinatorial mutations, and how you can construct new toric degenerations from old. So that will be the outline for this talk, and there'll be plenty of time for questions throughout the talk, so please feel free to ask, and I can pause at many points. Okay, so let's begin with polytopes and combinatorial mutation. So a little bit of background first. Where did combinatorial mutations come from? So in 2012, this is work by Akhtar, Coates, Galkin, and Kasperzik, when they were looking at classifying Fano manifolds using mirror symmetry. You can take a Laurent polynomial F, and we say it's a mirror partner if its classical period, if a Taylor expansion of its classical period it sort of coincides with a generating function for some Gromov-Witten invariance for X. And it turns out that there is a process on Laurent polynomials, which is some kind of mutation, which preserves the classical period. And in particular, for a family of Minkowski polynomials, the two Minkowski polynomials have the same classical period. So if and only if they're connected by a sequence of combinatorial mutations. From this, we get a notion of mutation for polytopes, which is induced by looking at the Newton polytopes. And this is what I'm going to be discussing later, but I'll be discussing it from the dual side, from the tropical side. Also, Nathan Ilton showed that if you take two polytopes and you look at their toric varieties, so these two polytopes, let's say, are related by a combinatorial mutation, then there is a flat family over the projective line such that there are two distinguished fibers, let's say 0 and infinity, which correspond to the polytopes, P and Q, toric varieties of these polytopes. So this gives us a way to sort of see how the toric varieties are related. And this is a bit closer to what I'll be talking about today. So I'll be interested in toric varieties too. And in more recent work by Escobar and Harada, they considered adjacent cones in the tropicalization of Grassmannian 2n and showed that there's some combinatorial way to go between the Newton or Konkov bodies arising in those cases. And in a appendix by Nathan Ilton, he gives a description of its relationship with the above notion of combinatorial mutation. So what I'd like to do now is give a description of what these mutations are, and I'll be doing so from the dual side, or on the n lattice side. So what's the setup? We're going to be working in some Euclidean vector space dimension n, and this has an inner product and a distinguished lattice, which I'll call Zn. So for me, lattice polytopes are going to be convex hulls of lattice points. For hyperplanes, I'll denote them HVH. So V is the normal vector and little h is the height of this hyperplane. And a primitive lattice point is just is a lattice point whose coordinates have a GCD1. So just a couple of pictures to show what I mean here. We have some hyperplanes, and we have a lattice polytope, which is the convex hull of a few points. You can get, if you take convex hulls, you can also get rid of some of those points. They might not be necessary. Okay. So with this we can define tropical maps and combinatorial mutations. So what are the ingredients that we need for a combinatorial mutation? We're going to fix a primitive lattice point W and a lattice polytope which sits in the orthogonal space to W. With these two pieces of data, we can define a tropical map. So this is a map from the space to itself. It sends each point x to a shift of x in the direction of W, and how much you shift by depends on the lattice polytope f. So it's given by x min. And I'll go through some examples of how x min looks in a moment. But if you restrict a tropical map to a polytope, and you note that the image is convex, then we say that you obtain a combinatorial mutation of your polytope. If the image isn't convex, then it's not a polytope anymore, so it might not make sense to call this a mutation. So a nice simple example. Let's have a look at a tropical map defined by this vector W, which is 1, 1, and this lattice polytope F, which is the convex hull of the origin and the point 1, -1. So what this tropical map does is it splits the plane into two regions, the region below the dotted line and the region above the dotted line. On the region below the dotted line, the tropical maps as the identity, so it fixes every point pointwise. And above the dotted line, it acts as a shear. So it moves every point in the direction W by an amount proportional to the distance that point is away from the dotted line. So for instance, the point 0, 1 is moved to the point 1, 2. In this case, if we focus on what happens to this unit square, it's the only point that's really moved is this point at the top, and we obtain a triangle, which we note is convex. So this gives us a combinatorial mutation of the square. So a couple of questions you might have at this point. Is the image always convex? And clearly that's not the case, because if I start with, say, a straight line that passes through the dotted line, then it's going to be bent out of shape by the tropical map, and the image won't be convex. And perhaps another question is, why do we call this a tropical map? Does this have anything to do with tropical geometry? And how can you see that? And the answer is yes. This x min might be something that you might consider related to tropical geometry. So let me explain how you will see that. Let's look at a slightly larger example. So this is in 3D. Take W to be the vector pointing upwards, and F is the convex hull of the origin, and two unit vectors. So how does x min look like here? So if I take a point x, y, z and look at min, it's going to be the minimum of 0, minus x, and minus y. And you notice that this doesn't depend on z. So I can take any slice of 3 space and it looks the same. So in particular, if z is equal to 0, this is how x min looks. It's 0 in this bottom left quadrant, and it's minus y and minus x respectively. And so this picture might look familiar to you as a tropical line in R2. So what does the tropical map do? So let's take a sheet of paper, and after applying the tropical map, you can see it sort of folds the paper in sort of 2 parts. So it folds it up in one way and folds it to the side in the other, and you get these crease lines where these orange lines are in the above picture. And in some way, this is what tropical maps look like in general. You sort of divide your space into different regions, and the tropical map is going to shear each of those regions in the same direction, but perhaps by different amounts. Okay. So this is what a tropical map is, and this is what combinatorial mutation is for me. What are some properties, say, that are preserved by the tropical map? So one thing that you can look at is the so-called Ehrhart Polynomial, and this is going to count the number of lattice points in dilations of polytope. So if I have a polytope, which is the convex hull of V1 up to Vk, then the nth dilation of P is going to be the convex hull of NV1 up to NVK. So it's a nice thing that if you count the number of lattice points inside the nth dilation, then this is going to be a polynomial with rational coefficients of degree d, where d is the dimension of your polytope. So it turns out that combinatorial mutation preserves the Ehrhart polynomial, and this is one of the results from Akhtar, Coates, Galkin, and Kasperzek. So we saw earlier that this square and this triangle are related by a combinatorial mutation. So they have the same Ehrhart polynomial. And on the right, I've drawn a different polytope which has 4 lattice points. But this has a different Ehrhart polynomial, so that tells us that it cannot be related to the others by a combinatorial mutation. And something else that might let you know that the right-hand polytope is not related to the first 2 via combinatorial mutation is that it has this internal lattice points, and you can't, if your polytope originally doesn't have any internal lattice points, it's going to be very difficult to obtain an internal one via combinatorial mutation. Okay. So what else can we do? Well, there are 2 famous polytopes associated to posets. So if I take a finite poset, I can define what's called its order polytope and its chain polytope. And I won't really use the definitions, but they're here for completeness. And so Higashitani showed that if you look at these polytopes, there's always a sequence of combinatorial mutations taking you from one to the other, and he gives a explicit construction of this. So why is this interesting from, say, an algebraic geometric perspective or algebra geometry perspective? Well, there are 2 famous examples of order and chain polytopes. There's this Gelfand-Zetlin polytope and FFLV polytope, which arise from finding, say, Toric degenerations of 5 variety. And turns out that they're also the order polytope and chain polytope, respectively, of a particular finite poset. And so this means that you can deform one polytope into the other by a sequence of combinatorial mutations. And this gives you a purely combinatorial way to show that they have, say, the same Ehrhart polynomial. In general, if I have 2 polytopes and they're related by a sequence of mutations, then we'll say that those 2 polytopes are mutation equivalents. So at this point, there are a number of questions that you might have about combinatorial mutations. So which properties, say, are shared by polytopes that are mutation equivalent, and associated to each of these polytopes, we have some toric varieties. What are the, are there any geometric properties, say, that are preserved by a combinatorial mutation? We've already seen that Ilton showed that you can find them as inside a flat family. So for the two examples that we've seen already, the one on the left here, the square, this is just a Segre embedding of product of projective lines in P3. And on the right, we have something that looks like a parabolic cylinder on an affine patch. So I invite any questions about combinatorial mutations at this point before I move on to talking about, say, toric degenerations, toric varieties. Let's start with toric degenerations. So if it's not familiar to you, a toric degeneration is going to be a flat family over the affine line, such that one of the fibers is a toric variety and all of the other fibers are isomorphic. If they're isomorphic to some given variety X, then we say that this is a toric degeneration of X to that toric variety. Why is this a useful notion? It's because if I take a variety X and a toric degeneration, then if I want to study particular algebraic invariants of X, then it's possible to do so over any fiber. In particular, I can choose the toric fiber. And if I choose the toric fiber, then I can exploit many of the nice relationships between toric varieties and their polytopes. There's a dictionary going between the two, or toric varieties and their fans. And this makes it a lot easier to read off these invariants. So if you're given a general variety X, you can ask, does it admit some toric degenerations, and what structures exist maybe to parameterize all of these toric degenerations? So in the case, so this is a very difficult problem in general. So we should start maybe by looking at some easier varieties. So the family of varieties, one of the families of varieties that I'm interested in are the Grassmannians. So a Grassmannian is, as a set, you can think about it as the set of all k-dimensional linear subspaces of Cn. And you can embed this and give this a structure of a projective variety by using the Plücker embedding. You can think about this as the vanishing set of this Plücker ideal, which I'll denote IKN, living in this polynomial ring with n choose k variables, one for each k subset of 1 through n. And what is this ideal? This ideal is the kernel of a map which sends each of these variables Pij to a maximal minor of some matrix of variables, which are called Xij. So let's begin a running example. So Grassmannian 2, 4. We take our matrix X to be this 2 by 4 matrix. And what's the Plücker ideal? It's going to be the kernel of this map that sends Pij to each of the 2 minors. So in this case, the Plücker ideal is generated by a single term. And so this is the polynomial. It's a homogeneous quadric. This is true in general for higher Grassmannians. They are all generated by homogeneous quadrics. Well, not necessarily one of them. There could be many generators. And so using this description, we can give a toric degeneration of Grassmannian 2, 4, where the fiber over T is the vanishing set of this polynomial. So in particular, if I look at the fiber over 0, I get the vanishing set of this irreducible binomial, and this is a toric variety. So how do we do this in general? So one way to do this is to use what are called Gröbner Degeneration. So these are degenerations that are going to be parameterized by some weight vectors in Rn. So weight. So if I take a polynomial ring in n variables and a vector in Rn, so I have then I call it a weight vector for R because each of the coordinates of W corresponds in some unique way to a variable of my polynomial ring. That means that if I take a polynomial in R, and here I just want to note that I'm using multi-index notation. So this x to the u means x1 to the u1 dot 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 xn to the un. Then this weight vector gives me a notion of a lead term for f. So this is going to be the collection of all terms of f that have minimal weight. And what do I mean by minimal weight? I mean that the weight of a term is just the dot product of u and w. Okay. I can do something similar for ideals. So if I take an ideal of R, then the initial ideal is going to be generated by all initial terms of all polynomials inside of f. And so it turns out that you can construct a flat family very close to what we want, whose special fiber is equal to the vanishing set of this initial ideal, and all the other fibers are isomorphic to a vanishing set of I. So that means that if I can find a weight vector that gives me a toric initial ideal, then I'm good to go. I've got a Gröbner Toric degeneration from Gröbner degeneration. So let's say we've got this ring R in 6 variables. Let's take a weight vector. Let's take a really simple one. So the only variable that has positive weight is P12. Take an ideal, let's say this principal ideal. The only term which has positive weight is P12, P34. This is going to have weight 1, and all other terms are going to have weight 0. And so that means that if I look at the initial ideal, is going to be this irreducible binomial. This is a toric ideal.
Ollie, there's a question in the chat. So is I assumed to be homogeneous here?
So in this case, I'm going to be working with the Grassmannian, and that's a homogeneous ideal. And yes, I do want to assume that I is homogeneous because I want to make sure that I can have Gröbner bases, and I'm only aware that you can have so this weight W, the lead term might not necessarily be a monomial, so I can have lots of terms be the lead term, and so I think that I want to make sure that these are homogeneous ideals.
Thanks.
Okay, so yeah, let me focus on the case of the Grassmannian. And how could we cook up weight vectors that give rise to toric degenerations? So one way to do this is to recall. So firstly, let's recall what is the Klucker ideal. It's the kernel of this homomorphism. Let's take a weight vector on the variables of this ring Xij. So you can think of V as being a K times N matrix. What I can do is I can pull this back to a weight vector on this ring in CPJ by saying that the weight of PJ is equal to the weight of the determinant, or the weight of the image of PJ under this homomorphism. How does this look like? Let's say I've got this matrix here, V, which is a weight vector for this 2x4 matrix. Then the induced weight vector for P12 is going to be the weight of x1, y2 minus x2, y1. So what's the weight of x1, y2? It's going to be the sum of 1 and 5. And the weight of x2, y1 is sum of 2 and 2. So just be the minimum of these two numbers. So if you play with this a little bit, you can show that for any polynomial inside of IKN, because it's the kernel of some homomorphism, then the initial is not going to be a monomial. And this is going to be important for what I say in a moment about tropicalization. And the other thing is that we say that if this weight vector v is generic enough, so that is to say that the initial term of each determinant is a monomial, then this induces what we call a matching field, a coherent matching field. And so the coherent matching field has slightly less data than, it has very similar amounts of data than is to have a point inside of Rk times n, such that each of these is a monomial. So for the time being, it's fine to think about a coherent matching field as a choice of weight vector for Rkn. So in particular for this example here, this matrix, you can go through and you can check that for every Pij, the determinant on those columns I and j will have a unique initial term. It'll have a monomial as its initial term. Okay. So this leads us sort of nicely to the idea of tropicalization. So this is going to be the collection of weight vectors. And so there are a few different definitions for tropicalization, and one that sort of fits nicely for us is going to be collection of weight vectors such that the initial ideal doesn't contain any monomials. And so we've seen that all matching fields give rise to points in the tropicalization, or for every weight that induces a matching field, that weight is going to be a point in the tropicalization. So using Gröbner degeneration, we have that a weight W gives us a toric degeneration if the initial ideal with respect to W is a toric ideal. So toric is equivalent to saying that it's generated by binomials and it's prime ideal. So in the case of small Grassmannians, Grassmannian 2n's, you can write down very nice characterization of its tropicalization. And so here's a picture for Grassmannian 2,5, so 2 planes in C5. The tropicalization, if you quotient bias linearity space and then take, say, intersection with a sphere, you'll get something that looks like Peterson graph. So each of these edges of the Peterson graph correspond to some maximal cones in the tropicalization. But for higher Grassmannians, so there's a famous paper by Sturmfels and Zelevinsky for Grassmannian 3,6 and explains how the tropicalization looks there. But for higher Grassmannians, it's still sort of unknown how best to think about tropicalizations. One way is to go through Dressians and so on. So let's suppose that we do have a weight and it gives us a toric degeneration. And in particular, let's say this weight comes from a matching field. How can we determine, actually no, before we do that, let's note one thing about matching fields actually. So not all matching fields give rise to toric degenerations. So the first place that this might go wrong, so for Grassmannian 2n, all matching fields give rise to toric degenerations. The first place it might go wrong is for Grassmannian 3,6, and Mohammadi and Shaw showed that such matching fields exist. They call some examples of these are the hexagonal matching fields. And so they defined a nice family of matching fields that give rise to toric degenerations for Grassmannian 3,6. These are so-called block diagonal matching fields. So I'm going to write down what are called the 2 block diagonal matching fields, and they're induced by this weight vector here. So you can, the most important part is of what's happening in the second row. You can see that it's if L is equal to 0, then you just get a sequence of decreasing numbers, and as L increases, you have 2 parts of decreasing numbers. And that sort of gives us some interesting structure to work with in terms of what the initial terms look like for all of the maximal minors. So this is the general definition of a two-block diagonal matching field, and it turns out that each of these gives rise to a toric degeneration for Grassmannian Kn. And in fact, even more is true. You can move to other families of varieties, including full flag varieties, and you can take a very similar approach and show that all of these weights give rise to toric degenerations there as well. But I'd like to focus on Grassmannian case today. And I'll note that if L is equal to 0, then you get this matching field B0, and this is sort of famously called the Gelfand-Zetlin degeneration. And so this arises in other parts from representation theory, GLM. Okay, so now that we have a family of matching fields that give us toric degenerations, how do you extract, say, the toric variety? What's a nice way of seeing that from the matching field? Well, what you can do is, if I pick, so if I have a weight vector V, which induces a matching field, then I can write down this monomial map here. So this monomial map is going to send each Pj to the initial term of the determinant. And from the definition of matching field, we required that each of these initial terms was a monomial. So this is a monomial map. The kernel of this is going to be some toric ideal. And it turns out that the weight that's induced by V, so this W here, the initial ideal of the Fluker ideal coincides with the kernel of this monomial map, if and only if this left-hand side is a toric ideal. So whenever we do have a toric degeneration of Grassmannian Kn, we can write down its ideal in a very easy way. This map psi lambda is very combinatorial, and in our family of examples above, it's very easy to write this down. So, and moreover, you can write down what the polytope is of this toric variety. You can just see that as the convex hull of the exponent vectors of the image of this psi lambda. So if you have a matching field induced by a weight, very easy to write down what is the polytope, what is the toric polytope for this degeneration. So let's see a running example. Let's say I've got my matching field B2, which is induced by this weight vector. And say I want to look at what happens to P12 under this psi map. Well, what is P12? What is P12 sent to? Which determinant is the determinant on the first two columns? And the initial term is going to be the leading diagonal term, because 0 plus 1 is less than 0 plus 2. So if you do this for all of the variables Pij, then you get a collection of these vectors. And if you take their convex hull, you're going to get a polytope. And it turns out in this case, let's say the F vector of this polytope is 6, 13, 13, 6, 1. And in some way, this is sort of the, for Grassmannian 2n, all of the matching fields that give rise to toric degeneration sort of give you the same toric variety. So in particular, this is the only F vector you'll see for Grassmannian 2n. Okay. So before I move on to our results of connecting combinatorial mutations and these ideas from toric degenerations, are there any questions about this part?
How general are toric degenerations coming from matching fields?
So in general, this is a good question. There are definitely points in the tropicalization which don't lie inside some matching fields, but I don't have a good enough grasp on the general tropicalization of the Grassmannian to know what those look like in general. So if you have a really concrete description of tropicalization, then you'll be able to get your hands on many other potential weight vectors. So in the case of Grassmannian 2.5 here, the cones that are going to give rise, or that have a good chance of giving rise to a toric degeneration, are going to be these maximal cones. So take its tropicalization, look at the collection of maximal cones. You should start with those. But yeah, there exist maximal cones that aren't parameterized by matching fields. So we have to be, it would be interesting to know what other objects exist to parameterize those cones. As far as I'm aware, there aren't any.
Okay, thanks.
Okay. So what did we do? Well, we were looking at, so first of all, I'm going to say by the GT polytope, I mean the polytope associated to the matching field B0. Okay, so this is the matching field where all of the initial terms of your determinants are the leading diagonal. Okay, so the results that we have are connecting these families of matching fields that I showed. So the first thing we've done is to show that, so for any two block diagonal matching fields, their polytopes are mutation equivalent. So we can find a sequence of mutations that take you between them. And we give an explicit construction of this. Moreover, what we do is we actually find a sequence of mutations that only pass through other matching field polytopes. So we so given two block matching fields, we give a so the sequence of mutations only pass through some other matching fields, and we call these sort of intermediate matching fields. And it turns out, or something else that we show is that if you have any other matching field and its polytope is mutation equivalent to the GT polytope B0, and you could replace this with any other polytope that arises as toric polytope for the Grassmannian under degeneration. If it's mutation equivalent, then that matching field also gives rise to a toric degeneration. So if you put these together, in particular the last 2 points, you find that all of these intermediate matching field polytopes that we find, these are also arising from toric degenerations of the Grassmannian. So in particular, we sort of expanded this family of matching fields to quite a large family now. And the other thing to note is that what kinds of tropical maps did we use along the way? The kinds of tropical maps we used here were actually quite simple to write down, in the sense that, so if you recall from the definition of a tropical map, the tropical map has two parts to it. It has the vector W, which tells you which direction to shear your polytope, and it has a factor polytope F that tells you how to split up your polytope. And for us, our factor polytopes in our construction are line segments, which are sort of the simplest you can get, which means that all of our mutations are split up the region into two parts. It acts by identity on one part and it acts by a shear on the other part. And using these kinds of tropical maps makes it very simple to show that for our tropical maps, they preserve the integer decomposition property of the polytope. So that is that in some sense, you can say that IDP property is equivalent to saying your polytope has enough lattice points. So when you define your toric variety from your polytope, then you don't need to move to some dilation of it. And this property is important for proving the third part of the above theorem. So how did we go about constructing such sequences of mutations and how did they look like, I've got some nice pictures to show you. So let's say you're going from B1 to B2, so 2 block diagonal matching fields. The way that we worked was to note that when you look at the definition of matching field polytope, it sits in a very large ambient space and it has many redundant components to it. So what we do to make our life easier is we project our polytopes down to a space such that they become full dimensional, and in that space we can write down our tropical maps explicitly, and then we pull back to a new polytope. And when we do this process, we're not altering the polytope in any way. These act sort of as isomorphisms on the polytopes and also reduce the dimension of the ambient space by 9. And so by composing all of these tropical maps, we get a mutation from between our block diagonal matching fields, but along the way we pass through all of these other matching fields, which sort of are interpolating between these two matching fields. And so what's happening at each step, sometimes it's very difficult to determine what's happening to the polytope at each step, because so we're trying to, at each step we're just sort of moving a couple of vertices at a time, slowly massaging one polytope into another. But if you wanted to study, say, how the phase lattice is changing, it's actually quite difficult. So say for Grassmannian 3-5, these are 2 examples of the vertex-edge graphs of 2 intermediate matching fields. The only 2 vertices that are really moving are the ones on this right-hand side in the blue region. But by moving those 2 vertices, you change the vertex-edge graph. So you remove these 2 dotted lines at the top and you add these 2 dotted edges at the bottom. So it's very hard to predict how things change in this way. Okay. So I think I've gone a little bit fast, so that's sort of where I wanted to leave it. I'm happy to discuss anything from the talk, and maybe we could have a chat about these things. But thank you very much.